So now that we have all the tools of vector geometry at our fingertips, in particular, we have this really powerful tool in the cross product to tell us, given two non-parallel directions in 3 space, it gives us a third direction which is perpendicular to them both. We want to be able to use that idea, that notion, to come up with ways of describing things like lines and planes in 3-dimensional space. So that's going to be the last thing that we do together today, and this is section 9.5 in our text. So I want to start with planes, and we'll talk about lines subsequently, but first I kind of want to set the table a little bit. So the kinds of equations that we write down for lines and the kinds of equations we write down for planes are going to be different in nature to one another. The kinds of equations we'll use for planes are going to feel more familiar. They're going to be scalar equations. We're going to see a plane as a level set, a level surface of a function of the 3 variables x, y, and z. So it'll be some function of x, y, z equals a constant. That's going to be what our equations for planes are going to end up looking like. Meanwhile, our equations for lines in 3 space are typically going to be what's called parametric. We're going to do a lot this semester with parametrizing, creating parametric equations that describe both curves and surfaces in 3-dimensional space. And so lines, which are our first example of a type of curve in 3-dimensional space, are going to be ones that we describe with a parametric equation. So that's just, I want to sort of plant a flag on that before we get started, that we're going to use 2 different types of equations for these 2 different tasks for the most part. So let's start with sort of asking ourselves, what kind of information do we need? What is a sufficient set of data for us to uniquely determine a line in 3 space or a plane in 3 space? So we need kind of 2 things, and they both are similar to one another in some ways. The first thing that we need is a point that our line or plane contains, that kind of sets the location of that object within 3-dimensional space. So we need to know, give me an example of at least one point that my line passes through, for example, or at least one point that my plane contains. So if we're using the example from the activity that we just did on cross products, we might pick one of those points, maybe 0, 1, 2, or something like that, as an example of a point that is contained in my plane. Maybe I'll use that same point as a way to motivate my line example also. Why not? Right. So knowing a point in my line or a point in my plane kind of sets the location of this object within 3-dimensional space. But then the other thing that we need to know is we need to know some data that can tell us the directionality or the orientation of our line or plane within space. And the good thing is, as soon as we have a point and a direction or an orientation, that's enough to uniquely define a line or uniquely define a plane inside of 3 space. The difference between the two is that a line is characterized by which direction it is parallel to, and a plane, as it turns out, is going to be defined by what direction it is perpendicular to. So that's the qualitative difference between the kinds of information and how we're going to use that information to uniquely determine a line and uniquely determine a plane. So our lines are uniquely determined by a point and what's called a direction vector. It's a direction to which the line is parallel. A plane is determined by a point and what's called a normal vector. Normal is yet another word that means the same thing as perpendicular, which means the same thing as orthogonal. Don't ask me why we have so many different words for the same thing in mathematics. But a normal vector describes the direction to which our plane is perpendicular. Another way to say it is that lines are determined, the direction of a line is determined by which direction it does go, and the orientation of a plane is determined by the direction it does not go inside of 3-dimensional space. So the good part is, though, that each of these can be uniquely determined by 2 pieces of data, each of which is a point and a vector. So in my picture of a line over here on the left-hand side, I might draw the direction vector of my line to look something like this, maybe, if I place the initial point at the origin, so that what we're looking at, right, is a line and a direction vector that are parallel to one another. Oh, sorry, I guess we don't use that notation for parallel in geometry. Usually it's, something like that. So the line and the direction vector are parallel to one another, which also means that if I were to take that direction vector and make its initial point P, so put its initial point right on my line, then that means that its terminal point will also be on my line. We're going to use that fact in a minute to determine parametric equations for that line inside of three-dimensional space. Let's pick some coordinates for this vector. I don't know, let's say it's 1, -2, 1, or something like that. All right, so a point and a direction vector are sufficient to determine an equation for a line. A point and a normal vector are sufficient to determine an equation for a plane. So let's use the normal vector from the example that we just did previously, right? A direction of a vector that's perpendicular to my entire plane was this vector that was the answer to your last activity, 2, 4, 4. So let's make 2, 4, 4 the coordinates of my normal vector. Sorry, let me keep my color coding here and draw my normal vector in blue. So this is a vector that is perpendicular to the plane. And so 2, 4, 4 will be the coordinates of this normal vector. So let's try and figure out, just from the data that we have here, how we might come up with an equation for a line which contains a given point and which is parallel to our given direction. And then also figure out how to use what we learned today about vector geometry to find an equation for a plane which contains a given point and is perpendicular to a given normal direction. So starting with the line example over here on the left, the key observation here is that if the initial point is on the line and I travel along any multiple, along any multiple of v, my direction vector, what I'm going to get is another point on that same line. Point on the line. Also a point on the line. So all the different points that exist on this line can be obtained by adding some multiple of my direction vector to this point that I know is on the line. So if I add one multiple of my direction vector to my point, and I get to, right here, just take one copy of this and place it right there, what I'm going to get is the resultant vector p plus v. So this is p plus v right there is another point. But then if I did it again, if I place another copy of this direction vector at that point as its initial point, and I add another copy of v, I'm going to go to p plus 2v. I can keep going. P plus 3v is going to be on this line. P minus v, so if I go in the direction opposite to my direction vector, that will also be a point on my line. So what do all of the points on my line have in common? All of them are p plus some multiple of v. And so an equation for this line, we can describe all the points on this line as my point, p, added to some multiple, and that unknown multiple I'm going to call t. Again, keep my colors straight here. P plus t times v. And since v and p here are both points, right? They're both vectors. This right-hand side, this equation here, is going to be a vector equation. And so it's going to be described by a function whose input is this parameter t. So you tell me how many multiples of the direction vector you want to use, and then my function is going to pop out a location, a vector, a point inside of 3 space, which lies on my line. So this is a new type of function. It's called a vector-valued function. It takes a scalar as input, but it spits out a vector at the end of the day. And so the name of this function is going to be it's going to be named with a letter which is a vector letter. So r with a vector on top of it will be the name of this function. So here is a form of parametric equation for this line, p plus t times v. And to better kind of understand what this is, we can just write it out in its components. So if p had the components 0, 1, 2, And v here had the components 1, negative 2, 1. This was v. So if I then multiply this v by my parameter t, then that's going to be t, negative 2t, t, right? And then if I add those together, that's going to give me a set of components for my parametric equation for this line, p plus tv. It looks like I got to make a little bit of room here, as I'm running into my branding and my logo down on the bottom. Sorry, Bridgewater. R of t is going to have components, and I'm just going to add 0 plus t, so that's going to give me t. 1 plus negative 2t, so 1 minus 2t, and then 2 plus t. And that's what we would call a parametric vector equation that describes the line which has a point 0, 1, 2, and which is parallel to the direction 1, negative 2, 1. So we can go forward from that information into a parametric vector equation. We could also, if you just gave me this parametric vector equation, I could read off of this equation a direction vector just by looking for the coefficients of t, right? Negative 2, 1, and 1, right? So there is my direction vector showing up as the coefficients of the parameter t in my parametric vector equation. Right? That's how I could have known that 1 minus 2, 1 is a direction parallel to this line. So that's the story for lines. Let's shift to the story for planes, because this connects more directly to the problem that we were just doing. So if I have a point on my plane that I know is on my plane, in this example 0, 1, 2, and if I know a direction that is perpendicular to my plane, how can I use vector geometry to come up with an equation that describes every point that is a part of my plane? In other words, if I have any other point at all which lies on my plane, let's call it Q, and let's say that the coordinates of that point are the unknowns x, y, and z. I want to figure out how to describe which x's, y's, and z's are going to lie on this plane. So I want an equation that x, y, and z are all going to satisfy. And I want to be able to use vector geometry to do that. And the only thing that I know is that the normal direction is perpendicular to this plane. So probably what I want to do here is just come up with a way of using, well, let me say it this way. What vector operation that we learned today is really good at detecting when two vectors, two directions, are perpendicular to one another? What's the easiest, the quickest way to tell whether two vectors are perpendicular? So the dot product is tailor-made for this, right? The dot product can tell us when two directions are perpendicular because it tells us that their dot product is 0. And so I need this normal direction, so my normal vector here, needs to be perpendicular to my plane. So I need a direction that is parallel to my plane in order to make this work. So what I want to do, to find a direction which is parallel to my plane, I'm going to do what you did in the last example. Since I know 2 points in my plane, one of which has specific coordinates, 0, 1, 2, the other of which has arbitrary coordinates that we're trying to characterize in this process, I can find a vector parallel to my plane just by connecting P to Q with a displacement vector. It doesn't really matter which direction we do that in, either from P to Q or from Q to P, but I think I like to do it as Q minus P, so it points from P to Q. So let's call this vector W or something like that. So if that vector is W, then W is Q minus P. And so its components are, in this example, x minus 0, y minus 1, and z minus 2. Right? And so that direction is parallel to my plane. Plane. Okay, so if that direction is parallel to my plane, and my normal direction, which is, 244? This normal direction is perpendicular to my plane, then when I take their dot product, the result of that dot product had better be W dot n had better be 0. So that's where the geometry comes in, right? That's how we encode perpendicularity into the algebra that we're about to write out. But I haven't actually performed that dot product. And when I perform that dot product, I'm going to get an expression which I need to equal 0 if and only if xyz is on my plane. And so just doing this dot product that's over here is going to give us the other side of this equation, which describes my plane. So to do the dot product, I'll just multiply the x components by themselves. So this x component is x minus 0 multiplied by 2. So that's just going to give me 2 times quantity x minus 0. And then I do the same thing with the y component, 4 times the quantity y minus 1. And with the z component, 4 times quantity z minus 2. Running out of space over here. Z minus 2. And then to finish the dot product, I just need to add all of those together. And so when I take a step back from this and look at what this equation, what the structure of this equation is, right, I have x minus blank, y minus blank, z minus blank, and those blanks are being filled in by the coordinates of my point, my p, 0, 1, 2. And then I have these coefficients, the coefficient of x, the coefficient of y, and the coefficient of z. And those coefficients came from the components of my normal vector. And so at the end of the day, just like with our line equations, we can read off the normal vector in a plane equation just by reading the coefficients of x, y, and z. When we read the coefficients of t in a parametric vector equation for a line, it gave us the direction vector of the line. When we read off the coefficients of x, y, and z in a plane equation, it gives us the coordinates of the normal vector to that plane, or a normal vector, rather, to that plane. So one quick and simple template that we can use, right, to find an equation for a plane which is perpendicular to a given normal vector and which contains a given point. I'm just going to rewrite this equation just so that we can make sure to have it in as readable a fashion as possible. So 2, 4, 4, my components of my normal vector, end up being the coefficients, rather, of x, y, and z. And then the coordinates of my point are just going to be the things that I end up subtracting from x, y, and z as a part of my equation. There we go. 4 times z minus whatever, and then equals 0. And so 0, 1, 2 are what fill in here. And then I've got pluses. There we go. So that's an equation for this plane. And if I wanted to make it look a little bit nicer, I could just simplify out all the algebra that's on the left-hand side. Let's just do that just for kicks. If I simplify out the left-hand side, I'm going to get a 2, a 4, and a 4 as the coefficients of my x, y, and z. Right, so 2x, 4y, 4z. And then I'm also going to get a bunch of constants, right? 2 times 0, well, that's 0. 4 times minus 1, and then 4 times minus 2. And when I add all those together, I'm going to get negative 12, I believe. And so on my left-hand side, I'll have minus 12 equals 0. And then I'll add 12 to both sides. And this tends to be the format in which we most often meet the equation for a plane, is it'll just be some linear function of x, y, and z on the left-hand side, in this example 2x plus 4y plus 4z. And the right-hand side is just going to be a constant. In this case, it would be 12. So we now have a recipe for finding an equation for any line inside of 3 dimensions. All we have to do is, again, focus on what information do we need. We need a point on the line, and we need a direction vector parallel to the line. Once we have that information, then this p plus t times v parametric vector equation will give us an equation for the line. For planes, we again focus on the 2 pieces of information we need, a point on the plane and a direction normal to the plane. The components of that normal vector form the coefficients of x, y, and z. And then to figure out the right-hand side, so this is another way we could do it, we could just write the left-hand side as 2x plus 4y plus 4z, and then plug in the coordinates of the point that we know is on the plane to figure out what the right-hand side needs to be. After all, 2 times 0 plus 4 times 1 plus 4 times 2 is where this 12 would have come from. Whew. So that was the overview of equations for lines and planes. And the only way to make these problems any more challenging is just to make you work a little bit harder to figure out this information, right? Like maybe you don't know the point up front, but you have enough information in the problem, in the setup, to figure out an example of a point that belongs to the plane. Or more commonly, you don't know the direction vector or the normal vector up front, but you have enough information in the problem to figure out what that direction ought to be. Similar to the last activity that we did in section 9.4, in that activity, the question was, tell me an example of a direction. Sorry, I'm trying to get it back in my camera here. Find a vector which is orthogonal to the plane containing these 3 points. In other words, what you found was a normal vector to the plane containing these 3 points, but you didn't know what that direction was. You had to do some geometry with vectors to find it, right? By taking displacement vectors and finding their cross product. But then once you have that information, everything from there is cookbook, right? We have these two sort of templates, a parametric vector template for line equations and a scalar equation template for plane equations that can get us to where we need to go.